thriving hacker community here in India. Thank you to the many of you who have gone out of your way to introduce yourself to me over the last couple of days. I really appreciate it, and I'm especially excited to see how much activity there is in this community in open source software and even a little bit of open source hardware. The fact that there are so many people here dedicated to open source is very exciting to me. I do open source hardware, that's all I do, and for my company, Gray Scott Gadgets. So I build some commercial open source hardware like HackRF and Ubertooth, and I also enjoy doing security research and putting these tools to use, and I especially enjoy research that involves making new hardware, finding opportunities where there's stuff that can be discovered with just a little bit of effort to make the right tool for the job. So this is one of those projects, and it's part of a loose organization of like-minded individuals who are putting together projects to demonstrate that tools used by the NSA and other nation-state actors are actually a lot more accessible than people might think. That we can build these things ourselves using open source hardware and software, using off-the-shelf tools. We can build all the same capabilities that are used by the largest governments in the world. And if you want to get a good overview of the entire NSA Playset project and kind of how we got started with it, I recommend watching my talk with Dean Pierce at Tour Camp last summer. It's online, and we go through the entire leaked catalog that the NSA Playset is inspired by and talk about our ideas for how these things could be built. And today I'm talking about RF retroreflectors in particular. And an RF retroreflector is something that uses this technique of RF backscatter communications. In this case, to eavesdrop on a target device or a target cable that carries some information. And the attacker transmits a radio signal directed at that target. There's a small implant that I'll talk about that is implanted in the target. It's very tiny and very minimal circuit. And then a reflection is picked up by the attacker and analyzed to determine what data was carried on that cable or the data that are within the device. So basically it's a radar technique. The attacker is using radar to illuminate an implant that reflects a signal back to the attacker. And I do want to kind of set something straight. There was an early article or two written about this project saying that I was reverse engineering stuff from the NSA tools, and that's not really true. I'm definitely inspired by some of the leaked classified documents, but I'm forward engineering. I'm creating my own devices and my own tools that are loosely based on things that the NSA has used. So what to expect in this talk is a little bit of leaked classified information, just those pages from the NSA ANT catalog that are relevant to RF retroreflectors. And then I'll be going over my hardware designs, and we'll do a little bit of a live demo or attempt a live demo here with one of my retroreflectors, and I'll talk about the successes that I've had. So this really is, a lot of this kind of stunt hacking stuff is just to lure you into the room so you can hear me rant about the state of emission security. You've probably heard a thing or two about emission security over the years, but I want to talk about active attacks versus passive attacks. Now, passive attacks are what you've probably heard about. You might have heard the code name Tempest referred to. This is monitoring unintentional emissions, unintentional radio emissions often, but they can be other kinds of emissions. Unintentional emissions from a target system, and using that passive monitoring, an attacker can often learn about the state of that system. And there's a fair amount of research into this type of passive attack. In particular, if you're interested in looking into this stuff, I highly recommend getting started with the various writings of Marcus Kuhn. But active attacks are something different. And active attacks are an area of research that I think is largely unexplored, surprisingly unexplored. The first known RF retroreflector using a kind of active emission security attack is called the Thing, or it was also called the Great Seal Bug. And it was found supposedly in the early 1950s in a wooden carving of the Great Seal of the United States that was hanging in the U.S. Embassy in Moscow. And it had been given some years earlier as a gift to the ambassador by a group of Russian school children, which I find to be a classic technique. And it was famously revealed in 1960. It was revealed to the public during the U2 hearings. The U.S. government showed everyone that this had been found. And it's a wonderfully simple device. I don't have a schematic or anything, because there really isn't much to it. All it is a microphone and an antenna. I mean, that's literally the entire circuit. It's a condenser microphone, which changes its capacitance as the air pressure changes, connected to an antenna. And the Russians would illuminate the thing with a radar transmission and pick up the reflection, which would carry an analog modulation that was based on the room audio, so they could listen in to the audio in the room. Wonderfully simple design, ingenious. For its time, it was really incredible technology. It was deployed sometime around maybe 1945-ish, and for that time period, this was an amazing, amazing technique. This type of technique has been used, as far as we know, over the years, but very little has been publicly known about these techniques since the Thing was revealed in 1960. Well, fast forward to a little over a year ago, and the ANT catalog, the NSA ANT catalog, was released, and it had things like this. RageMaster is a tiny little implant that is an RF retroreflector. It works very similarly to the way the Thing worked, except this time they're not monitoring audio, they're monitoring a video signal in a VGA cable. And the device is so tiny that it actually fits inside a VGA cable. And it can be illuminated with something like this radar, also from the ANT catalog. It transmits a very simple signal in the direction of that retroreflector, picks up a return, and then can deliver it to something like this, which is just a video screen so that somebody can watch what's on the target's screen. And there are other retroreflectors in the catalog, like Surly Spawn here. And again, it's quite small. I mean, this board is a little less than 1 square centimeter. And this is used for monitoring keystrokes, and is probably implanted actually in the keyboard. And it says it can work with both PS2 keyboards and USB keyboards, which is pretty cool. Here's another one, even smaller, Tawdry Yard. And this one is just a simple beacon. It doesn't actually eavesdrop on any data. It just allows the person with the radar, the operator, to detect its presence and maybe find its location by aiming the antenna differently. And here's one, Loud Auto, which is an audio retroreflector. This is like a modern day thing. It's just like the Great Seal Bug, except it's actually even smaller and using modern electronics. So, getting back to emission security here, I told you a little bit about the Thing revealed in 1960 and the ANT catalog that was leaked at the end of 2013. In between, we had 53 years of rumor and speculation. We had no real solid public information and no research into active emission security attacks. I haven't been able to find a single academic paper on the subject, a single HackerCon talk on the subject until I started looking at this about a year ago. And I think this is insane that we don't research this area, especially with the tools we have today, like software-defined radio. It's more accessible for us to experiment with ourselves, whether we're independent researchers or academics, or maybe you belong to a hackerspace that wants to do some interesting projects. There's a lot to do here. And now some say otherwise. Some say that during that 53 years, there's lots of information, and they'll point to some declassified documents that have a lot of hints about these types of technology, but they're just hints. There's nothing solid. Nobody's done an actual demonstration or shown exactly how some system works in that entire 53 years that I've been able to find. And so I say POC or GTFO. And I hope that more people will join me and try to prove some of this stuff and figure out what is possible. Now, the one brief mention I found in an academic paper was based on, I believe, a leaked, or not a leaked, but a declassified East German document, I think, from the 80s. And it said that they could irradiate a keyboard cable with some frequency and then detect key press codes in the retransmitted signal. So that sounds very much like what we're talking about. Although, interestingly, it doesn't say anything about any implant installed in that cable. So it's possible that the technique that's being referred to here was actually an attack of a radar against an unmodified device with no implant installed, which is highly interesting to me. So post-ANT catalog, I've been working on this stuff, and there's one other experimenter who's been posting videos on YouTube, GBPPR, look that up and you'll find some. And that's about it, I think. But I'm hoping that more people will pick this up. A quick note on the nomenclature. The ANT catalog uses the term retroreflector with a hyphen, but the word in more common usage outside of the NSA is without the hyphen, so that's the way I use it. And arguably, it's a little bit of a misnomer for this technology, but I use it because it seems to be so well established in the intelligence community. So a retroreflector is something that reflects a signal back to the source. And the example I like to use is optical or visible light retroreflectors are actually quite common. You see them on road signs, for example. They're coated with a retroreflective coating. So when you shine your headlight at a road sign at night, most of the light from your headlights bounces directly back in your direction. And if you're off to the side of the light source, you won't see the sign light up as brightly. So it's a very useful technique to make road signs much more visible at night to people who are near their own headlights, which of course is every vehicle pretty much. And so that's a good example of retroreflection, where the reflection is actually directed back towards the source. The retroreflectors that I'm talking about today aren't actually so directed. So the signal that's coming in gets modulated, but the reflection doesn't go in any particular direction. But we still call them retroreflectors, even though that might be a little bit of a misnomer. These things are using a technique of communication called RF backscatter. And this is a very well-studied method of communication. It's originally, I think the first paper I've been able to find is Communication by Means of Reflected Power by Harry Stockman in 1948. Notice, 1948, this is the very first paper on RF retroreflection, and it happened after the Great Seal bug was deployed. So that gives you an idea of how amazing that technology was at the time that bug was deployed. There's a lot of research over the years into backscatter communication and doing it more efficiently, effectively, different ways. The more modern research in this area is primarily in RFID technology. And there are different types of RFID. A lot of the RFID that you're accustomed to, like the type of tag you might have in your wallet, is a very short range technology, but there are longer range RFID systems, in particular those in the UHF bands, that use techniques very much like what I'm doing with the retroreflectors. So in order to use these things, we have to have some kind of a radar system. We have to be able to transmit a radio signal at the target and then receive the return and analyze that return. So what kind of radar systems might we use? One would be an off-the-shelf radar gun. I've done this successfully myself, just with a radar gun that I found on eBay, an old police radar gun. But it operates well above 20 gigahertz. So it's way above the frequencies that are mentioned in the ANT catalog, like 10 times the frequencies mentioned in the ANT catalog. And it's higher frequency than is convenient to work with low-cost radio tools. So it's not the best technology to use necessarily. But I found this Hot Wheels radar gun, also on eBay. These are great. And this is a toy radar gun that is actually a radar gun. And it operates at about 10 gigahertz. If you open it up, there's basically three sections. There's a battery pack in the grip, and then you'll see a little cable that runs from that grip back to the back of the thing where there's a little control board. And then there's another little cable that runs from the control board to the big tube. The tube is the radar, and it actually has a small circuit board on the back of it. And all you really need is the tube. All that control circuit stuff, you don't need it all. All you have to do is put a power supply up to the tube, and then and it has a baseband output that you can plug into an oscilloscope. And this is actually how I illuminated one of my, I think my very first RF retroreflector and got a successful return off of it, was with a Hot Wheels radar gun. You can find them on eBay, at least in the US, you can find them on eBay for around $25, $30, something like that. However, oftentimes they don't work. But what I found is that the failures are almost always on that control module that I cut off anyway. So the actual radar unit within the device has been reliable in every single unit that I've gotten off of eBay. It does operate at around 10 gigahertz. Oh, and go to that URL for some good tips on how to open up the device and hack with it. It operates around 10 gigahertz, so it's still kind of higher than most accessible radio tools other than this itself, but it provides a baseband output, which means you can analyze it with even a sound card or an oscilloscope or pretty much any tool you have to analyze an electrical signal. There are similar radio modules available that are even less expensive. If you search eBay for Arduino radar, you'll find a number of really low-cost radar modules that are highly similar to the one that's inside the Hot Wheels radar gun. And I found these like shipping from Hong Kong for $5. So really affordable technology is out there to experiment with this stuff. Another thing you might want to look into is the coffee can radar project from Dr. Gregory Charvat and some of his friends. You might have heard about a class that's done at MIT and Lincoln Labs. And this is a really cool project that lets you build a low-cost radar that is analyzed by a sound card. However, a sound card actually isn't fast enough for a lot of the stuff that I'm going to be showing. So it's a good thing to look into, but if you were going to try to build a custom radar for this application, you might need to do some kind of a data acquisition at a higher rate than your sound card can do. So I've been doing most of my experiments with HackRF. HackRF1, it's a software-defined radio platform that's well suited for this and many other applications. I like it because I designed it, and so I'm biased. But it works really well, and it's open source hardware. So if you believe in open research and open source, and you think that that's the right way to go for this kind of stuff, then it's definitely a good platform to look at. It is a software-defined radio peripheral, plugs into your laptop or other computer, and it's over USB. And it operates over a very wide frequency range from about 10 megahertz, well, really from about 1 megahertz up to 6 gigahertz. And that covers much more than just the range that is mentioned in the ANT catalog that the NSA uses for their retroreflectors. So it's inclusive of that range. And it has 20 megahertz of bandwidth, which is somewhere around 1,000 times the bandwidth or the bit rate that you can get with a sound card. So it's a much wider bandwidth technology, and it lets me eavesdrop on very high rate data signals that I wouldn't be able to do with the sound card. It's a half duplex transceiver, so it can transmit or receive, but not both at the same time. So in my demo up here, I actually have two HackRF1s. One of them is transmitting, and the other one is receiving the return. So I put them together in this, very sophisticated mounting apparatus, and I like these antennas, these directional antennas from Kent Britton, and he designs these PCB antennas. He's in Texas in the U.S., and he does a lot of these great designs for printed circuit board antennas that are low cost and easy to manufacture and very portable. So like getting them through customs in my laptop bag is relatively easy compared to a lot of other directional antennas that are much bigger. It does have a little bit of a problem in that, like compared to the coffee can waveguide sort of technique, I do have a bit more kind of crosstalk directly between the antennas instead of the reflection that I'm looking for. And so sometimes I'll put like a piece of metal in between to shield them from each other. That's a kind of a quick fix. But they work, other than that, they work quite well for this application. The frequency that I'm using for my demo here and for most of my experiments has been 2482 megahertz. And I know that's kind of a very specific frequency, but there's a reason why I have arrived upon this as a good frequency for experimentation. One is that the NSA, according to the ANT catalog, uses frequencies between 1 gigahertz and 2 gigahertz, and they were in the process at the time of the data from the ANT catalog, which is a few years old. They were kind of building a new radar that would operate in 2 to 4 gigahertz. So that whole range, 1 to 4 gigahertz, is kind of the range that the NSA thinks this is an effective technique for. And in the middle of that range is the 2.4 gigahertz band, which happens to be an ISM band or an unlicensed band in pretty much every country. So you can get away with a lot. Woo, that's fun. You can get away with a lot in the 2.4 gigahertz band because devices operating in that band are supposed to accept interference, accept the fact that they have to compete with other devices in that band. So you're going to not get into trouble transmitting at low power in that band compared to what you might get into trouble doing if you were in other bands in pretty much every country in the world. It also happens to be in the frequency band which is much broader than 2.4 gigahertz, but throughout the 2 gigahertz band, the HackRF actually performs best. That's the range that it performs best in, and it has the least emissions in other frequencies. So I get the cleanest signal, least likely to interfere with anybody if I operate in the 2.4 gigahertz band. And it's easy to find filters and amplifiers, off-the-shelf stuff that people use for Wi-Fi, for example. So if you do want to like amplify your signal, I don't necessarily recommend that you do that unless you really know what you're doing, but you can find low-cost, easy-to-use filters and amplifiers for that band. And also, the reason I am at 2482 and not anywhere else in the 2.4 gigahertz band is that 2482 is at the upper end of the frequency range that's designated for ISM use. And it's above the highest Wi-Fi channel, at least it's above the highest Wi-Fi channel that's permitted in the US. And it's also above the highest Bluetooth channel. There's a little bit of a range there right at the top of the ISM band where it doesn't get much use. So it's fairly empty, and I don't get my experiments interfered with by neighboring devices very much. So it all kind of works out that this is a good frequency to use for these experiments. The first retroreflector I made is a conga flock, and it's much smaller than a square centimeter. It is a little circuit board that has a component on it, and those two long wires, well, they're not very long, but those two wires form a dipole antenna. And so this is actually an effective retroreflector that you can plug into basically any electrical signal on a target device. And all you have to do is wire it up to the target device, and then you can fire radar at it, and from your return, you can recover the electrical signal that was on the target device. And you may be wondering why this thing is so gigantic. It's so huge. It is so huge because, well, for one thing, the circuit board that I originally designed was too small for my circuit board manufacturer. So I made it twice as big and put some silkscreen text on it. It's also so large because I put extra pads on it for experimenting with modifying the circuit a little bit, even though there's really only one component populated most of the time. And the other reason is that I actually wanted a printed circuit board. You could build this thing without the circuit board and just wire the, solder the wires directly to a transistor, but it won't be as durable. So really quickly, I'm going to go over the schematic, and it's super simple because you can ignore that unpopulated resistor. You can ignore these two that are just there for, based on how that signal is fluctuating, it switches on and off the path between the two antenna elements. That's all it's doing. And so it doesn't require any power as long as the target voltage is within the range that activates the transistor. And it's super simple and easy to build. I wanted to give away some for people to build at DEF CON, and so I made 1,000 of these and gave people the components they needed to build them at DEF CON. I have some left over, so if you find me later today and you want some of this stuff, I have some of this stuff, including the transistor that I like to use. I have a couple hundred of those with me, so if you want one, come get one after the talk sometime. And all you have to do is just solder the two antenna wires to it, solder the MOSFET on the board, which is the transistor, and then just solder connect it to the target that you want. And so here's an example of it connected to a cable that I wanted to monitor the signal on the cable. So then I started building these devices that are specifically for a particular target device. I'm just going to put this. Thank you. A particular target technology. It's a little bit inconvenient to kind of wire in or solder in this conga flock into any old cable or device. For experimentation, it's nice to just be able to plug in your retroreflector. So it's much bigger than it needs to be, but it has the plugs. And this is the one that I actually have a demo set up here for. Flamenco Flock is the code name here, and it is for a PS2 keyboard connection. And what I'm looking for is I want to be able to recognize a signal on that cable. And there's a clock signal on that cable, which I'm ignoring, and that's the upper plot in this graph. And then there's a data signal, which is what I'm actually tapping. So for example, and I just found this image on the internet, this is the signal that I should see on the wire if the letter Q is pressed on a PS2 keyboard. And so you see those kind of 3 short downward spikes and then the 1 long downward pulse. So that's the pattern that I'm going to be looking for. And this demo I don't think is going to work, but I'll just show you. What I do is, my hastily set up demo here, I'm just transmitting a CW signal with one hack RF, and then I'm receiving it with the other hack RF. And if I try to trigger on it, I should, theoretically, if I hit this key, I should pick something up. But I don't think I am. So I'm going to show you the same demo, but just with some data captured earlier instead in my lab, instead of trying to do it live. And what you should see is I was holding down the Q key and trying to capture there. Do you see that pattern? The 3 downward pulses and then the 1 long downward pulse? That's the letter Q being pressed repeatedly on a keyboard. And I'm recovering that electrical signal from the PS2 cable using this radar technique. So the next one I built, where are my slides? There. So that's what the waveform looks like. And the next one I built is Tango Flock for monitoring USB connections. Again, it's an inline USB thing with plugs to make it convenient for experimentation. And I was able to monitor low-speed USB. Now, low-speed USB devices include things like keyboards. So if you wanted to do like an RF retroreflector keylogger, we have one for PS2, we have one for USB. Now there are other rates of speeds of USB devices, and I've had a little bit of success. I haven't actually pulled any data out of a full-speed transmission, but I think it could work. High speed, I don't think would be very useful unless you had an extremely high bandwidth radar system. So I don't have a way to experiment with high speed USB. And super speed USB, which is brand new, is definitely out of reach of this type of technology. You're not going to be able to recover individual bits going over a super speed USB cable using this technique. But you might be able to monitor activity, for example. And then the last one that I've built is Salsa Flock, which is a VGA cable, VGA retroreflector, similar to Rage Master, but in this case is with convenient plugs for experimentation again. And when I get a signal from the VGA cable, when I get that return, you see how there are those like tufts of activity, and there's a little gap in between each kind of burst of activity. That gap is the vertical sync. Now this is where the high bandwidth, that 20 megahertz bandwidth of the hack RF, becomes very useful, because the VGA signal is about that much in megahertz. And I'll just show you I took that signal, that radar return, and like saved it to a bunch of bytes of the amplitude. And I just opened that up in an image editor. And the GIMP has this cool feature where if you give it arbitrary data, you can just like interpret it as a big block. And you have to kind of guess as to what your width is going to be, the screen width in pixels, and which doesn't necessarily correlate exactly to the screen width in pixels of your target device, because this is actually more related to the radio characteristics, of the sample rate of my return radar. But you can definitely see as I try different widths, there's some kind of pattern there. There's definitely some periodicity in what's going on. And if I keep going, then oh, look at that. This is an image from a screen, and you can actually see that this file is full of all of these screenshots, over and over and over again, because that screen is getting displayed over and over and over again on the target device. So this is an actual image from a target device in my lab that I recovered using the VGA retroreflector. The countermeasures, I don't have a whole lot to talk about because I don't think we understand this technology well enough yet. We don't understand the attacks well enough to really talk intelligently about appropriate countermeasures or effective countermeasures. But I hope that in the future we will. And I hope that some of you are intrigued a little bit by this area of research and think that you might be able to take part in this too, one of the best tools for doing this stuff is software-defined radio. And my slide is out of date. It says video series coming soon. Video series is happening now. I have 7 videos up online. I teach an in-person SDR class, software-defined radio class, at events around the world from time to time, and I'm putting that content online in an open content license through a video series. And I have 7 videos up already. The 8th video is on my laptop and will be posted as soon as I edit it. So that's going on right now, and I hope you'll learn a little bit about SDR and maybe do some of this research yourself. But before I go, I want to kind of show you, I think we're only scratching the surface of this type of reflective radio attack research. What I'm showing you today is intentional illumination. I'm firing a radio signal. I'm intentionally illuminating a device that is intentionally reflecting a signal back to me. But remember, there was that mention in a paper where there may have been an intentional illumination of an unmodified device, an unintentional retroreflector. So that's one of those other boxes in this grid. Nobody's done any demonstration that that type of thing is possible. That would be a really interesting area of research. And then there are those other boxes, like what about unintentional illumination? What about the target device? Somebody walks by it with a cell phone, and that cell phone illuminates the device, and then the receiver could passively receive that reflection from the unintentional illumination. And then you could also even have, theoretically, unintentional illumination of an unintentional retroreflector. Nobody is doing research in these areas yet, and I think it's extremely important for us to understand the security of our own devices and the devices we produce and help people use to really understand the security implications. We need to do more research in these areas. And if you do some of this stuff, be a good neighbor on the spectrum. Try not to interfere with anybody. Know your laws. I want to say thanks to some folks. And the NSA Playset project as a whole can be found at nsaplayset.org. Some of the information on the retroreflectors is not there yet, and that's my fault. But you can look and see my own GitHub account has all my hardware designs that I talked about in this talk. And of course, you can find me at greyskygadgets.com. And do we have time for a question or two? Sure. Anybody have a question? Here's one. Microphone's on its way.
I just had a question considering your background in music and looking at the musical instrument created by, it's called the theremin, which somehow, like, I mean, Leon Theremin was a musician, and and then he was kidnapped by the KGB. And is this sort of similar as well, like the theremin as a historical antecedent of?
Definitely, and I don't know if I mentioned it, and perhaps you know this, but the Great Seal Bug was supposedly invented by theremin. Yeah, I mean, he's best known today for the instrument that is named after him, that uses a little bit of a similar technique where it's actually using kind of a signal. Well, it's not exactly it is a radio signal that you're modulating by moving your hands around, antennas basically, and it makes the woo kind of sound that you might remember from such hits as Good Vibrations. It's a really interesting musical instrument, and theremin probably, it was probably through experiments with that kind of thing that led him to create the Great Seal Bug. We don't know a whole lot about that time of his life, but it's pretty cool that possibly his experiments in creating musical instruments using radio actually resulted in a major breakthrough in radio communication technology. And today, all of RFID systems could be traced back to that development. It's pretty cool.
I have two questions. One of them is that the only difference between an audio retroreflector and a normal bug used by NSA or anyone else is that this is only activated when a radio is being used, right? A radar is being used.
It's only active when it's in use, when...
No, like it's only transmitting when you're illuminating it with radar power, right?
I see, right. In my case here, and in all the cases that we see in the ANT catalog, yeah, the retroreflector is not transmitting any signal. There is no signal being transmitted over the air until the attacker actually fires up the radar, right? That's what you're getting at?
Yeah.
Yeah, so in some ways, this makes it particularly stealthy, right? Which is a good thing to point out, that a lot of bugs, a lot of radio bugs actually transmit a signal all the time, or they transmit a signal periodically using their own power source and their own transmitter. And so detecting those types of devices is a very different proposition than detecting one of these retroreflectors. You're never going to detect a retroreflector unless two things happen. One is the attacker is actively using it, and you see that radio transmission, or you pick up that radio transmission. Or the other is you actually try to illuminate it. You experiment yourself, or you do a sweep where you, and so I am talking about countermeasures, but you do a sweep where instead of just trying to detect signals, you actually transmit signals at a wide range of frequencies and try to see if there's any correlation in the return to figure out if you might have implanted retroreflectors or unintentional retroreflectors in your equipment or in your environment. And that technique of sweeping is very difficult to do correctly, especially if you have limited knowledge of how these devices work and what types of devices might be deployed. So that's why I think that this attack research is so important, that we try to build these things and we try to see how they work, and we try to create examples that then we can use to learn how we can detect these things, and how this technology is very accessible for people who want to start experimenting with it, but it's not accessible yet to just people who want to take advantage of what we've learned to protect themselves. And how does let's say a government agency, let's say an embassy, how does an embassy actually sweep for this type of device? Now, a lot of the government agencies probably have classified programs for doing this kind of thing, but then there are a lot of folks who could really benefit from that, who don't have access to those classified programs. So, yeah. Did I answer your question?
What?
Did I answer your question at all?
You did. Okay. So the other thing is, but being stealthy, you won't have data history, right? Like what happened before that. Unlike usual bugs, which have some form of recording device, you'll only get what is being used at that exact time, right?
Sorry, I didn't quite follow you.
Sorry. So you won't have data history, right? So as in, you will only get what is being spoken at, or what data is going through the wires at that exact time, right?
Oh, right. Yeah, that's correct. Right. I'm not retrieving data from the past. I'm not retrieving data from the hard drive or the laptop or anything. If I'm just sniffing the keyboard here, all I get as an attacker, all I get is the information about what keys are being pressed during my radio transmission, right, and nothing else. Is that what you're getting at?
But from the NSA side, isn't that a bit the opposite of surveillance? Because surveillance should be constant, right?
Arguably, but there's we don't know a whole lot about how those technologies in the ANT catalog are used or deployed. They may be things that aren't used hardly at all. We don't really know. They're just things that exist. And so Is it the best way to monitor a keyboard? Probably not. But in certain cases, it may be extremely valuable to be able to, for example, implant a tiny retroreflector that's extremely hard to detect into some keyboards, something that can last forever. There's no battery to run out. There's no power source required. So there are certain advantages to being able to use this technology as opposed to a technology that might be more effective at capturing all the keystrokes, but has different characteristics of detectability and longevity.
Any more questions?
Hi. I wanted to know if cost is not a concern, what is the maximum effective range of these radar devices, both the the one that transmits and the one that receives? Or if you have a transceiver, full duplex communications capability, what's the effective range?
That's a good question. What's the range? What's the distance? As you can see, the demo that I set up here, I'm only operating at about a half a meter, right? Which is not very much, but it's a good proof of concept. But the effective range really depends on primarily the transmit power. And I'm transmitting at very low power. I'm transmitting at a lower power than like all of the cell phones in this room. I'm transmitting at a lower power than a typical Wi-Fi device. And I do that because I don't want to get into trouble. I don't want to interfere with anybody. So I'm using an ISM band and I'm transmitting at super low power. And even at that extremely low power, I'm doing something like 10 milliwatts. At 10 milliwatts directional, I'm able to get a half a meter, no problem. And I've done experiments with the same equipment in my lab up to maybe 2 or 3 meters, but I haven't really explored what the maximum range is I could get. If we wanted to explore the maximum range, I should have killed my screensaver. If we wanted to explore the maximum range, then what you would need to do is actually amplify the signal and have a higher power transmission. And unfortunately, that's difficult to experiment with legally. So oftentimes I tell people, just don't amplify. If you can possibly avoid amplifying, just don't, unless you have a license and really know what you're doing. Or if you are going to experiment with amplified systems, do it in a Faraday cage. Well, unfortunately, a Faraday cage is limited in size, so for range testing, that doesn't help you. But primarily, it's a function of power, and so if you just add a lot more power, you should be able to add a lot more range. And government agencies, like intelligence agencies, they probably don't care a whole lot about whether they're interfering with somebody other than just to avoid detection. That's probably the only thing they worry about. And they don't have to necessarily follow the same rules that we have to follow. So unfortunately, it's hard to experiment with, but I would estimate that this type of a setup with more directional antennas, like bigger, maybe dishes or big waveguides, coffee cans at the very least, this type of a setup with better antennas and with amplification, I would guess that I could get hundreds of meters with very, very little problem.
But it's safe to say that this is a close access technology, eavesdropping technology. It requires you to be within close access to your target.
Yeah, it's definitely not something that's going to be effective over many miles, but hundreds of meters I think is very, very plausible to achieve without any great effort.
We have time for one more question.
One more.
I was really curious, how does retroreflectors work theoretically? Like you place something on the device and then it reflects the signals, right? Mm-hmm. What if someone plays another noise which actually gives some other signal to kind of obfuscate the actual data and then kind of mitigate this issue? Is it possible? by replacing some of
Are
the
you
device?
saying like as a countermeasure?
Yeah. kind of.
Yeah, that's a good suggestion. Could you just transmit some noise as a countermeasure to try to interfere with the attacker? And I think that is an area that should be researched. I think it could be effective. However, it does run the risk that your noise transmission actually gets reflected. And a smart attacker could theoretically kind of isolate the original transmission from the reflection, correlate one against the other, and like if you know a little bit about digital signal processing, the autocorrelation algorithm might be very effective for an attacker to then be able to just passively eavesdrop. So you'd have to be really careful with a jamming technique like that to experiment and ensure that what you're doing makes life harder for the attacker and not easier. But it's definitely an area that I think should be researched. Well, thank you all so much for coming. This has been a lot of fun.